Ladies and gentlemen, I am really humbled to be here on stage right now after this very impressive lineup of recipients of prizes and fellowships. And it is a very special pleasure to be able today to discuss with you and present to you some of the recent developments in solar energy and in photovoltaics, because I believe photovoltaics should not be neglected as part of photonics. Photonics is the interaction of light with material, and we should not only consider the emission of light from electricity, we should as well consider the opposite effect, which is photovoltaics. As a matter of fact, today I will not talk with you about mainstream photovoltaics. Mainstream photovoltaics meaning silicon-based photovoltaics, where we talk about increasing efficiency limits from today 16 to 18 to 20 to 22. World record stands at 25.6%. I would like to talk with you about much more exciting areas of efficiencies and materials technology, which bring us already very close to 50%. And at the end, I will show you one of the most recent results. I do my work with the co-workers at the Fraunhofer Institute in Freiburg. Fraunhofer is a very unusual national laboratory because Fraunhofer Institutes, and there are 66 of them in Germany, have a very different business principle. Basically, they are left alone to earn their own money. In my case, the institute with an 84 million budget has only 15% of basic financing from the government. The rest we have to earn ourselves through contract research. So we have to work under the same rules as any faculty member here in the United States. The only difference is, of course, that we are bigger, we are more flexible, and we can, of course, use this in order to develop strategies based on what we think is very exciting. And, of course, we are not only in Germany. When I came to Freiburg from 23 years here in Berkeley, I immediately said we need to found as well something in the United States. So we founded the the Center for Sustainable Energy Systems in Boston, CSE, and just last spring I was in Santiago de Chile. You know, Santiago de Chile in Chile is one of the most sun-rich countries of the world, and there we founded the Center for Sustainable Energy Technologies of Chile. Okay, let's go into the physics of solar cells. You know that the current market is dominated 90% of all solar cells which are being sold, and the market is very large today. We sell annually 60 gigawatts, 60,000 megawatts of solar cells, and 90% of this is out of crystalline silicon. Crystalline silicon is a fantastic material. As you all know, it's basically converted diamond. You just replace the carbon atoms of diamond by silicon atoms. And of course, therefore, we have a very stable material. The mainstay of microelectronics is as well the main pillar of photovoltaics. But the physics shows us, as you see on this picture, which shows the solar spectrum and superimposed what we can harvest by silicon photovoltaics. And you see we have two shortcomings. First of all, any photons which have a energy below the band gap go right through silicon, and this is the transmission losses on the right-hand side. Right at the band edge, with crystalline silicon, we achieve almost 100% efficiency, because when the photon just makes a valence band to conduction band transition, this creates electricity close to 100% efficiently. However, if we come to shorter wavelengths photons, like 2 electron volt photons, we only harvest for each photon 1 exciton, and at the end 1 electron volt of energy. So these so-called thermalization losses of the carriers as they fall down from excited states to the ground states in the conduction and valence band, they as well eat a lot of efficiency, so that Shockley and Queisser already a long time ago said any single material can have not more than about 32% efficiency, and for the data of silicon, this ends up at 29% efficiency. We are today with the best solar cell, which is a heterojunction structure from Panasonic, at 25.6%, so already coming close. And in the market, we have already high-efficient silicon solar cells of about 22% efficiency in mass production. So this is a story which comes close to a glass ceiling. And the question is, what can we do to reach higher efficiencies? And of course, we can make use of the beautiful opportunities offered to us by compound semiconductors. Compound semiconductors cover the full spectrum of optical wavelengths, and with the right combination of compound semiconductors, we can indeed harvest the light from a very wide spectrum. The only problem is, and this is shown in this graph as a vertical scale, we have a trouble creating structures of different compound semiconductors because of the difference in lattice constant. And this gives us severe restrictions as to which combinations can work, because we should never forget a solar cell is a minority carrier device. The task in a solar cell is to save the minority carriers generated by light before they hit a majority carrier, recombine, and they are lost. And therefore, any problems with defects, interfacial defects, everything what can make enhance recombination and increase the surface recombination velocity is very detrimental. And therefore, photovoltaics is one of the most exciting areas of materials research because it's so incredibly demanding to make really minority carrier devices which are coming close to theoretical efficiency limits. One of the structures which is very popular by now are triple junction structures, like the one shown here, based on a germanium substrate, and then gallium indium arsenide and gallium indium phosphide can be grown, and this can achieve already pretty impressive efficiencies. The best lab cell with a triple junction, 41.4%. The problem of these structures is, of course, they're extremely expensive to grow. The structure, as you see, not only needs the three materials with p-type and n-type conductivity, but in between you need as well tunnel junctions to bring the carriers from one material to the next. And of course, at each of these layers, at each of these interface, utmost care for defect-free structures is absolutely essential. And therefore, making such structures is very expensive. It can be done for solar cells to be used in space. And as a matter of fact, I have asked Picard why he didn't use for his famous plane which goes around the world these high-efficiency solar cells. The problem was that he is financed by one of the companies involved in silicon solar cells, and therefore he could not make use of the double high efficiency he could use with this kind of technology. I find this not a very good excuse if you think about the hype which is being made. So what do we do on Earth? On Earth we have to use concentrating technology. This means we cut our wafer, which contains hundreds of these cells. We can cut them down to a size of 2 by 2 square millimeters, place them under a concentrating lens so that the light of the large area of the lens, it can of course be as well a concentrating mirror, is concentrated on the solar cell and converted with the high efficiency of the solar cell to electricity. Physics helps us because the number of recombination channels in each given material is limited. And therefore, if you use only one sun without concentration, these recombination centers can be quite dangerous. But if you concentrate 100, 300, 500 suns, then the recombination channels are bottlenecked. They cannot efficiently recombine as many carriers as they could do in relationship to the carrier density in one sun. So the efficiency of solar cells increases with concentration, and therefore this technology not only is needed in order to make cost-efficient modules, it helps as well boosting up the efficiency. And as a matter of fact, you see the history is quite impressive, coming up the ladder, and this is now mainly 3-junction cells, which entered the 40% range already a few years ago. Now we have, of course, options to go beyond what is the limitation of the lattice constant. You know, we can make lattice match structures, then we are, of course, very restricted. We can make strained pseudomorphic structures, which we can extend the range of possible lattice constants for a little bit more. But then we have as well the option to use completely new technologies. And the two new technologies which are important is lift-off technologies, which allows to reuse a wafer substrate, and wafer bonding technology. When
the working group at ESE came to me and said, we want to use wafer bonding to make solar cells. I said, I am very skeptical that this will ever work, because in wafer bonding, you create an artificial interface. And of course, this might work well for silicon technology, where at the end, the carriers stay in the active layer near a field effect transistor. But in a solar cell, where the carriers have to go through the whole structure from top to bottom, they have to go through this artificially created bonded interface. But as I will show you very soon, this bonding, wafer bonding technology is today at the level we need in order to be able to make high-quality solar cells. So now we have, of course, a wide range of material. We can go away from germanium substrates to gallium antimonide substrates. We can use engineered substrates. This is what I will talk about a little bit more, where we can grow structures on two different substrates, optimize them, and then bond them together, forming one structure and at the end one solar cell. So this is the germanium-based 4-junction solar cell. You see the spectral efficiency data from each of the different layers. What is very important in such a structure is a so-called current matching, because whereas the voltages which you create from each of the layers when you shine light on the structure simply add up, the current has to go through the whole structure. And this means it makes no sense that in one layer you could create 13 or 14 milliamps per square centimeter. If in another layer you get only 9 milliamps per square centimeter, the weakest link determines the current. And you see, one can do a very good job in current matching. Current matching simply involves to match the thickness of the individual layer, because the amount of current created by light depends, of course, directly on the thickness of the layer. And if this is done very diligently, you get a good result as we see it here. And as a matter of fact, with this, one can come already to quite nice efficiency values. You see in the lower picture, 36%. You see the increase with concentration. The decrease to higher concentration factors has to do with the thermal management of the cell. That means if you want to run a cell at 1,000 suns than at 500 suns, you have to do much more in terms of taking away the excess thermal heat. And if you don't do this for any given structures, you get this type of maximum as we see it here. Now we come to a gallium antimonide based 4-junction solar cell. You see the gallium antimonide layer is the weak link. Here we have a very poor current matching because we don't get the same amount of current, but you see we can harvest solar energy far out into the infrared till about 1,800 nanometers. And with such a structure, 29% was the highest efficiency possible. The really most exciting structure, which is the holder of the current world record, is a 4-junction solar cell on an indium phosphide type structure. You see here the transmission electron, the scanning electron microscope cross-section. In the scanning electron microscope, you of course recognize only large areas. Very critical for bonded structures is to look at the quality of the interface, if there are bubbles and things like that, and therefore the scanning acoustic microscope turned out to be a very valuable characterization tool to see the quality of these layers. And this is how these indium phosphide-based cells are being made. The indium phosphide layer itself is not an indium phosphide substrate, but it is an indium phosphide on gallium arsenide engineered layer. And you see the two structures, gallium indium phosphide, gallium arsenide from one side, gallium indium arsenide phosphide, gallium indium arsenide on the other side, and then wafer bonded together, and one can even use the lift-off substrate on top several times for subsequent growth runs. And you see in the TEM cross-section, the right bottom part, how high is the quality of the interface. And these are the results of the optical analysis. You see very, very good high quality current matching of all the 4 layers. This is pretty much a feast, interaction between simulation and experiment. And these are the results, and the small circle doesn't look very exciting. This is a current world record of the conversion of solar light into electricity at 46.1% at ESE, 46.0% at AIST, the sister institute in Japan, which did the calibration together with ESE. So we have exceeded 46%. And we believe that we are very well on our way towards 50%. The structure itself has a maximum of the order of 60%. So there are still possibilities, and in any case, I would say it is an amazing number which can be reached in this technology. Now let us go a step further, because these are structures grown on 3-5 type of materials. But what about silicon? We have all these investments in silicon PV technology, and silicon is dominating the world. Wouldn't it be fantastic to be able to break out of the glass ceiling of the efficiencies available on silicon with a hybrid solar cell which uses the experience which we have collected in making silicon-based solar cells, but adding up the experience which we can gain from 3-5 cells. And the key issue there is using wafer bonding. We avoid the problems of the growth of 3-5s on silicon. So wafer bonding, and you see here the cross-section, that this interface really does not introduce any defects in the adjacent layers. This is really a key factor. Oh, by the way, this was in the wrong order. This shows, I should have had this one slide before. This shows where we are currently. For those who are not in the PV field, this chart is the most important chart for anybody working in photovoltaics. It shows the different technologies of solar cells, and you see the time evolution of efficiencies. You see, for instance, down in the right corner, the very steep and quick developments of things like perovskites, but we are at the moment right on the top with the 46% cell I showed you before. But now let's come to the silicon-based PV. This picture we have already seen, and of course, if we could combine silicon with additional materials which harvest more efficiently the short wavelength range, we should be able to achieve more than 30% efficiency. And using the wafer bonding process is the key element in this development. We can grow 3-5 on one side, we can combine it with a crystalline silicon solar cell, and we use wafer bonding in order to create one structure, a two-terminal device, which can be used at the end of the day like any silicon solar cell. Of course, we need to use the experience which has been gained in wafer bonding in the silicon world. 200 millimeter wafers can be today bonded without any problems, and larger diameter wafers are being worked on. This is a technology which is already well established. The key is, of course, to do this with the utmost cleanliness, because particles, moisture are really very dangerous and very difficult. And you can measure it by measuring the conductivity through the interface. 3 times 10 to minus 3 ohm square centimeter is a very good value for this. And you can look at the quality of the bond. This is a picture similar to the one you saw before, where the interface, which is artificially bonded together, is really a quite perfect interface. Again, I was proven wrong. A man-made interface can today be good enough to let the minority carriers come through without big losses. So then, of course, come the optical simulations. This was a first step in such an optimization, and then by adjusting the structure, one can get more and more out of it, increase the efficiency in order to reach the best possible result on such a crystalline silicon solar cell. And one has as well to make tricks with technology, substrate etching. This is described here. As you see, it shows how we can improve the carrier lifetimes, and this, of course, is at the end the key factor for the solar cell efficiency. And at the end, we can put it all together. We can have the improved effects of the good substrate etching. We have to make sure that we are not damaging in the process the rest of the structure in order to harvest the best current in all the parts of the device. And another effect which we can use in silicon and which we have good experience with in silicon is light trapping. In silicon solar cells, the surface is textured so that it effectively traps light and allows through back reflection that the efficiency gets higher than it would be if the surfaces would be just flat. So this gives another 2 milliamps per square centimeter boost in the silicon side. You see here such a textured wafer. You see the contacting with an aluminum foil, a technology which was developed at my institute. It turned out that contacting with an aluminum foil is almost as good as depositing an aluminum layer, but of course it interferes much less, it gives much less recombination centers. You bond the foil with a laser at thousands of bonding posts across the wafer, and in this way you guarantee the good electrical contact. I hope I could show you that the understanding of materials combined with the understanding of processing technologies, and there the big advantage is the combination of experiences from silicon technology, from 3.5 technology in the best way, using the 3.5 deposition experience which we have, growing lattice matched as well as strained layers, using wafer bonding coming out of silicon technology. This gives us a tool chest, and you saw it in the structures which I presented to you, which allow us then to really come forward and exceed everything what was known up to now and really reach the efficiency limits that theory sets us. And I think having solar cell conversion efficiencies near 50% is really something even people who are very, very skeptical about photovoltaics have to acknowledge we are on the right way. So I showed to you several structures of 4 junction solar cells, which we can realize by wafer bonding. The detailed materials understanding combined with sophisticated engineering of all components, and it helps to have in one institute, in our institute, 1,100 people, half of them about working in the solar cell area, where we have the right experience coming together to be able to achieve such a feast. The 46.1% is already a well-established world record, but what we are very proud of, and I don't say a secret by telling you that this year my time as ESA director will come to an end, because in Germany, in contrast to the United States, we have mandatory retirement, and I could extend my retirement age for a few years after my 65th birthday. So I consider this last result, which will be published pretty soon widely, as a very nice present for being able to have served as ESA director for 10 years. So I'm very, very impressed that we can now present more than 30% crystalline silicon solar cells. It was a pleasure to share this with you. Thank you so much for your attention.
Good afternoon, ladies and gentlemen. It is a great pleasure and honor for me to be here and allowed to share with you the fascination about motions confined to smallest dimensions in space and time. I thank the organizers for the possibility to discuss in front of such a distinguished audience how attosecond physics now provides real-time access and real-time insight into electron-light interactions underlying a wide variety of phenomena in science, technology, and medicine. The work I'm going to present has been done at the Max Planck Institute of Quantum Optics and the Ludwig Maximilian University, certainly not by myself, but by a number of great co-workers and collaborators whose invaluable contributions I very gratefully acknowledge here. I also thank Mandy Singh, Dennis Luck, Christian Hackenberger, and Woogieworks Animation Studio for the graphics and animations in my presentation. The story of attosecond physics started a long time ago but I need to cut it short in order to be able to address its presence and future. The groundbreaking work of Professor Towns, Prokhorov and Basov allowed the first laser to be demonstrated back in 1960, which was followed very soon by the birth of nonlinear optics, which in turn permitted the generation of ever shorter pulses by laser mode locking down to a few femtoseconds by the mid-80s. The titanium sapphire laser, chirp pulse amplification, and Kerlens mode locking combined this unprecedented temporal confinement of radiation with high fields and average powers, giving birth to novel disciplines such as femtochemistry, high field physics, and attosecond science. Processes underlying real-time control and interrogation in chemistry are governed by cycle averaged quantities, such as the amplitude envelope and frequency sweep, both encoded in the complex amplitude highlighted in blue, the complex amplitude of the electric field, shaking electrons with subatomic amplitude over many field cycles in the regime of perturbative nonlinear optics. By sharp contrast, high fields, strong light fields are able to induce large-scale, multi-atomic unit electron excursions within an individual field cycle, as exemplified by above-threshold ionization and high-order harmonic generation. The resultant sub-cycle electron trajectory control constitutes a conceptually new way of quantum control, fundamentally different from schemes relying on multi-cycle interactions. This strong field quantum control requires control of the light force, of the electric force of strong light fields within the wave cycle. To this end, first we need to confine radiation substantially to a single wave cycle. This was enabled by a group delay control over a full octave by aperiodic multilayers, briefly chirp mirrors, giving rise to near single cycle light with a well-controlled amplitude but uncontrolled field oscillations. This deficiency was removed by using the Nobel Prize-winning frequency comp technique of my colleague and collaborator, Theodor Hensch. Here you see the temporal evolution of the force exerted on electrons by the electric field of the first waveform-controlled pulses generated and measured back in 2003. The resultant controlled force, controlled light force, enable sub-cycle control of electron trajectories, and this is the basis of attosecond metrology. A textbook example for strong field sub-cycle electron control is the generation of isolated attosecond pulses by means of optical field ionization of atoms and subsequent high-order harmonic emission. The first process releases an electron wave packet from its atomic binding. After a several nanometer excursion, this wave packet is pulled back to the vicinity of its parent ion by the next half cycle of the field, where its interference with the bound state portion of the wave function of the very same electron results in high frequency charge oscillations emitting a short burst of XUV light. This XUV light lasts just a fraction of the driving wave cycle. If the field consists of many oscillation cycles, what the interaction produces is a train of attosecond pulses, which has also been successfully used for a number of beautiful experiments by Anne Luile and her team, as well as other groups, but unfortunately I will not have time to address those experiments here. I will focus on the use of isolated attosecond pulses. Strong field subcycle electron trajectory control does not only allow the reproducible generation of isolated attosecond pulses, but also their temporal characterization in the attosecond streak camera, first proposed by Paul Porkum and experimentally demonstrated by Reinhard Kimberger and co. in Vienna. The laser waveform and the XUV pulse delivered by these two collinear beams depicted in red and violet are delayed with respect to each other by a two-component mirror, as well as also focused to an ensemble of atoms, in our case neon atoms. The electrons released from the neon atoms by the XUV pulse are, depending on their moment of release, accelerated or decelerated by the strong laser field, changing their momentum by an extent that is proportional to the vector potential of the laser field at the moment of birth of the electron. This relationship between the momentum change and the moment of birth maps the temporal profile of photoemission and thereby that of the XUV pulse to a final momentum distribution of photoelectrons. Recording these XUV radiation induced and laser field streaked photoelectron spectra as a function of delay between the XUV pulse and the laser field yields an attosecond streaking spectrogram, which allows complete retrieval of both the temporal evolution of the electric field as well as the complex amplitude of the XUV pulse, which can meanwhile be generated routinely with durations down to 100 attoseconds and below. These experiments demonstrate how strong field subcycle electron trajectory control makes the basic tools, the attosecond varying light force and the attosecond duration radiation available for real-time observation and control for control of electron light phenomena, such as, for instance, optical field-induced electron tunneling in real time. If induced by a single cycle pulse, the intensity of which you can see at the bottom right, the ionization in this case of krypton atoms is confined to a fraction of a single half cycle of the ionizing field as captured by attosecond transient absorption spectroscopy. The slow motion replay that you have seen here has been implemented with a temporal magnification of 10 to the 16, corresponding to the combined magnifying power of the world's largest telescope, currently under construction in Chile, and the state-of-the-art electron microscope. If we are asked what attosecond metrology is good for, we may choose to answer that it does basically the same job in time as a telescope and the electron microscope are capable of doing jointly in space. But why do we actually bother to create such a colossal temporal magnifying power? According to Max Planck, the more delicate the details are by which we can follow nature on any path, the richer and more lasting will the gain be that we are able to draw from this perception. The rest of my talk will be devoted to a few examples in the pursuit of grand questions from disparate fields. Does the time-dependent Schrödinger equation work well for more than one electron? What are the consequences of electron-electron interactions? What is the ultimate speed limit of electronics, and how can dissipation, which is behind a decade-long stagnation of the clock rate of digital electronics, be actually overcome to approach this limit? What are the electron-nuclear dynamics behind vital biological functions and those initiating their life-threatening malfunction? And last but not least, Can ultrafast science be possibly instrumental in combating cancer? Electron correlations pose a major challenge to modern quantum physics. Meanwhile, they can be accessed in real time, even in the simplest model system for electron correlations in helium, for which Joachim Burgdorfer and co-workers recently numerically solved the full 2-electron time-dependent Schrödinger equation. They predicted, somewhat surprisingly and counterintuitively, that attosecond photoemission can release an electron from a helium atom more rapidly if the second electron gets also excited. That's what is referred to as the shake-up process, as compared to the process leaving behind the helium ion in its ground state. That's what we refer to as the shakedown variant. Simultaneous attosecond streaking of both processes by Martin Schulze and co-workers confirmed the predictions, the quantitative predictions of these ab initio calculations to within an accuracy of better than 1 attosecond over quite a range of excitation photon energies. This remarkable sub-attosecond agreement between theory and experiment furnishes atomic chronoscopy with an accurate time zero marker and allows the technique to test and help refine modeling of electron correlations in complex systems which are beyond the reach of ab initio calculations. Modeling microscopic dynamics would also benefit from improving computing power by expediting electronic signal processing, ideally towards optical frequencies. This would rely on a dramatic reduction of energy deposited during a switching cycle, which of course requires insight into the energy transfer between optical field and matter, described by this simple integral. In wide gap systems, the linear polarization oscillates perfectly in phase with the driving electric field, zeroing the net cycle averaged energy transfer. A net energy flow then depends on a nonlinear polarization that can possibly be induced at increased field strength. The direction and the magnitude of the energy flow then depends on the timing, on the precise attosecond timing of this nonlinear polarization with respect to the driving field. Attosecond methodology now allows us to measure this timing. To this end, Ann-Kathrin Sommer and co-workers passed a few cycle pulse through a thin silica sample and measured the transmitted waveform at low and here in the focus at high intensity at strong field strength. Both measurements have been performed by attosecond streaking. The difference between the two normalized waveforms is directly proportional to the nonlinear polarization induced by the strong field, providing direct access to both the amplitude and the phase of the nonlinear response of the electronic system. We have dubbed this technique attosecond polarization spectroscopy. As you might have noticed, in this technique, both pumping as well as probing is now performed by the oscillating electric field rather than by the amplitude envelope of the pump and the probe pulse. And in this sense, the technique can be regarded as a generalization of pump-probe spectroscopy. Here you see the measured nonlinear polarization of silica near breakdown. And you recognize that it is slightly lagging behind the driving electric field by less than 100 attoseconds, which, quite remarkably, is dramatically dependent on the electric field strength. It decreases very, very rapidly if the field strength is decreased, in this case, from 2.6 volt per angstrom down to 2.1 volt per angstrom. Equally remarkably, this delay turns actually negative by the trailing edge of the pulse. The nonlinear polarization precisely known, together with the driving field precisely known, we can now calculate the attosecond nonlinear light electron energy transfer, which you see here. The initial positive delay of the nonlinear polarization with respect to the driving electric field implies a net energy flow from the field to the electronic system needed to remove the electrons ever farther away from their field-free location. Upon returning to their equilibrium position, they radiate back part of the absorbed energy into the driving field as reflected by a negative delay of the nonlinear polarization on the trailing edge of the pulse. Near breakdown at a peak electric field strength of 2.7 volt per angstrom, a substantial, actually even dominant fraction of the transferred energy is irreversible by the field. This irreversible energy transfer is related to a multiphoton-induced conduction band population that is evaluated as a tiny fraction of the density of valence band electrons. The fraction is actually so small that this conduction band population is hardly measurable by any other means. In spite of its low value, this strong field-induced conduction band population is of utmost importance, is really crucially important for scaling electronic signal processing towards terahertz and possibly even petahertz frequencies, where even a small amount of this population generated upon each switching cycle would rapidly accumulate upon subsequent switching cycles and lead to intolerable dissipation. Fortunately, a moderate decrease of the electric field strength by as little as 25% decreases the irreversible energy transfer dramatically, actually below our current detection limit, whilst leaving the reversible part of the energy of the transferred energy that is useful for signal processing nearly unchanged. Attosecond polarization spectroscopy will explore the optimum interaction regimes for petahertz scale optical signal processing. It has also revealed the buildup of free carriers in the conduction band of an insulator within less than 1 femtosecond near the highest field strength, which actually opens the door for optical field sampling up to petahertz frequencies with a solid-state device. This is something I'll come back to in a few moments. Last but not least, attosecond polarization spectroscopy also uncovers the picometer attosecond scale nonlinear motion of electrons, in this case valence electrons. But we should also notice that the mean electron excursion evaluated here does not really provide insight into subatomic scale or atomic scale electron rearrangements that might happen in complex systems, such as, for instance, biological molecules following some excitation. These rearrangements can only be observed by diffraction imaging with correspondingly short attosecond X-ray or electron pulses. Their generation in turn would require increased bandwidth and strength of the controlled right force. Attosecond shaping of electromagnetic forces with an increased bandwidth could recently be demonstrated by Eleftherios Goulalmakis and co-workers with a chirp mirror-based optical waveform synthesizer. Seeded with a 2-octave phase-stable supercontinuum, this device can generate a wide range of optical waveforms, including sub-cycle, sub-femtosecond optical transients for the first time. Attosecond shaping of electromagnetic forces has so far relied on titanium sapphire-based fused-cycle laser technology and the complex vacuum beamline for sampling the waveform by means of attosecond streaking. Next generation attosecond metrology will draw on tailored ultra-strong light forces synthesized by multi-channel optical parametric amplifiers of multi-octave continua and, in our vision, sampled by a solid-state petahertz waveform recorder. Hani Fatahi and co-workers are now using a 1 kilowatt picosecond ytterbium YAG laser to pump OPA broadband OPA channels in the visible, near-infrared, and mid-infrared, seed them simultaneously with one and the same phase-stable multi-octave continuum to allow coherent combination of their outputs to synthesize a wide range of ultra-strong multi-terawatt waveforms, including near 1 femtosecond 30 terawatt pulses at a 5 kilohertz repetition rate. Ultra-strong force or field synthesis within attoseconds will permit, according to simulations at this point, the generation of several angstrom wavelength X-ray harmonics, which will pave the way towards attosecond diffraction imaging. This may also soon become reality with the help of electron wave packets. Katrin Kielhofer, Peter Baum and co. Recently demonstrated tenfold compression of temporal compression of single electron electron pulses and their temporal characterization with the controlled field of single-cycle terahertz light. Scaling the technique to more rapidly varying fields in the infrared holds promise for picometer attosecond resolution electron diffraction, hopefully in the foreseeable future. As a first application, the optical field controlled single electron wave packets have been used for imaging the spatial distribution of terahertz fields in a bow tie antenna, as you see here. Electron microscopy of optical fields may be quite useful, may be very instrumental in advancing electronic and optical signal processing, hopefully similarly instrumental and useful as a solid-state instrument for sampling optical fields up to petahertz frequencies. The enabling technology here is what we have already discussed, the strong field-induced injection within a 1 femtosecond, or actually less than 1 femtosecond interval of carriers into the conduction band of an insulator, in this case silica. The optical field to be probed, to be sampled, can then separate the created electron hole charge carriers and drive a current in an external circuit. This current can be measured as a function of delay between the carrier injection and the optical field to be sampled. Using electro-optic sampling of infrared fields, actually down to a wavelength of about 1.2 micrometer, as a benchmark, Sabine Kaiber, Nick Karpowitz, and co-workers have succeeded in testing and also validating nonlinear photoconductive sampling for retrieving optical waveforms up to petahertz frequencies. Petahertz waveform sampling together with few cycle infrared light will also open new prospects, or actually is about to open new prospects for biology and medicine. Measuring the frequencies of molecular vibrations by infrared absorption and Raman scattering offers a global molecular fingerprint for cancer and other diseases in clinical samples. Here you see how the electric field evolves in a pulse generated by a powerful near, well, let's say few cycle octave spanning mid-infrared source near 10 micrometer, developed by Joachim Pupetzer, Oleg Pronin, Jens Biegert, and co-workers. The source actually allows to be transmitted through aqueous solutions of molecular absorbers. The source is intense enough so that we can fight with the source and we can defeat actually water absorption. And the field you actually see here is the result of basically the transmission through such a sample. And direct field sampling, in this case by electro-optic sampling, allows the detection of extremely weak signals radiated from the molecular absorbers over many picoseconds, thanks to the femtosecond confinement of the excitation, permitting a virtually background-free signal detection. Petahertz bandwidth nonlinear photoconductive sampling will extend this capability to stimulated Raman scattering. Here you see how already partial fingerprinting of blood sera by conventional frequency-resolved infrared spectroscopy over a limited spectral range by using a simple two-dimensional principal component analysis allows discriminating cancer patients from healthy individuals in a pilot study led by Michaela Sigman and Sasha Apolonsky. Petahertz bandwidth optical field sampling will permit for the first time the acquisition of complete phase-sensitive fingerprints by field-resolved infrared and Raman spectroscopy over the entire range of molecular vibrations, holding promise for early detection and possibly even diagnosis of cancer by risk-free screening and a cost-effective therapy monitoring. Ladies and gentlemen, attosecond metrology has now proven its ability to resolve hitherto inaccessible electron light phenomena. Its next generation, with its powerful multi-octave light transients, all solid-state petahertz bandwidth metrology, and attosecond X-ray and electron pulses, will open new frontiers in physics, technology, and medicine by resolving fundamental condensed matter electron phenomena, advancing signal processing to its ultimate speed limit, gaining insight, providing insight into dynamics of complex biological systems, and hopefully exploring the frontiers of light-based fingerprinting of cancer for early detection of the disease. The most exciting part of the story of attosecond physics is certainly still ahead of us. It's definitely worth joining in. Thank you.